Alrighty then. Hey guys, what's going on? Memes here. Yes, we're back. I erased the board this time. I actually tried to start thinking ahead and everything. You know how that works. Okay, I can hear myself in my ear, so that means for some reason I did some weird audio control and it seems to have fixed the audio. It's the stupidest thing in the world. Set this driver to this, but you set this program to this, and then it stops effing up. Technology. Fantastic. As long as it works and there's not too many gremlins, hopefully. All right. So, what are we talking about today? Today, we're going to talk about a couple of desirable clickbait thingies. Because who doesn't like black holes, neutron stars, and of course the Planck density, and what may or may not be in common with this? I feel like I may have mentioned this in passing at one point, and then I didn't really look into it because there appears to be okay, maybe I should have just done the Planck spring constant. Maybe that was a smarter way to go about this. Oh well. Let's go to our thumbnail because, well, we made it. Lazily taking a picture of the Google auto-generated response and everything. Let's share with the class here. What the heck are we even talking about? All right, this guy over here. As we can see, not to bury the lead, black holes, neutron stars, and the Planck density. As we can see here, the generic description, the Planck density, rho sub p, because rho is the physics thingy that we usually use for density. It's that funky shaped little p there. All right, it's a fundamental unit of density, approximately 5.155 times 10 to the 96 kilograms per cubic meter, which is 93 grams per cubic centimeter. Frickin' dense. It is among the highest imaginable physical densities, roughly equivalent to compressing the entire solar system's mass into a space of a single atomic nucleus. Right. So basically taking an atomic nucleus. All right. A proton, like 10 to the minus 16 meters. It's a million billion times smaller than like the scale that we're on, like the meterish scale there. And you would have to take the mass of the entire solar system and cram it down into just a single nucleus. What? Why? How the heck could you even do that? Well, that's because the Planck density is so ridiculously ginormous. Like the sun is like, was it like 10 to the 30 kilograms or something like that? Yeah. And this is a Planck mass, so basically the mass of a mote of dust within a Planck volume. How small is a Planck volume? 10 to the minus 105 meters. Redonkulously small. So you have like a cubic meter of suppose you have like a cubic meter of water. Okay, let's do this. You got. Oh wait, I have a board. What's going on, Orion? Good to see you, my friend. Thank you for joining. All right. Let's suppose you have 1 cube. Okay. I'm gonna draw the square. We're gonna draw the other square. Attempt to do that little middle school illusion so it kind of looks like a cube. All right. So this is 1 meter cubed. All right. Now, if this was water, so we're going to say conventional water density. Density. All right. So assuming conventional water density, this would be 1 meter. That'll be 1,000 kilograms. Boom. Okay. So you got that meter. All right. 1,000 kilograms, that's more than me. But now, take the mass of a mote of dust. This is 1 meter. You want to have the Schwarzschild black hole, the minimum black hole, according to Professor Susskind, the Planck mass represents a minimal black hole. That is the limit. All right. So we're going to go all the way down to Planck. What's it going to be? Planck. Let me get another marker. Should probably buy some new ones. Like I got these ones. Oh, God. Where did I get these? Austin, maybe? Planck. All right. Scale. All right. So we go down to the Planck scale. We can have another cube. All right. Not to scale. Should probably put that. Not to scale. Should probably. Some of like for me, sometimes I take things very literally. He doesn't need it. There we go. All right. Note. There we go. All right. So this would be. All right. So this is about 10 to the negative 105 meters cubed. Okay. And this would be about 10 to the minus 8 kilograms. All right. Kilograms. Boom. Okay. So we've got that. Now, why am I showing you this? Because if we notice, 10 to the minus 105. Okay. Just whatever it might be. We've got a 105 there. We've got an 8 there. Okay. If we were to rig-a-jigger this, so we did this mass divided by this volume, you would have basically just take 10 to the minus 8, and now you're dividing it by a much smaller number, 10 to the minus 105. Guess what that's going to give you? You divide a small thing by a redonkulously small thing, you're going to get a really big thing. In this case, it would be the Planck density. So basically, in these units, these are our units here for our coherent-based system. These units, these are the limits. So Planck mass, the maximum mass you can fit within a minimum volume, okay? That happens to be the density, because guess what? Long story short is the math that you do is, if you're dividing this by that, the difference between 105 and 8, it's going to be about, it's about 97-ish. But depending on, again, we dropped the first couple of digits. Yeah, it's about a 96 difference between 105 and 8, assuming there's some pre-factors there, and there are. You want to take a look at them? All right, came up with a theory. You can always send me things. I'm always interested in looking at different things. I've also got at least one of the chat things set up with enough history of reviewing papers, being like, all right, let's keep it within generally known physics. Be open to ideas. Generally, we're going to give weight to some more credible sources, but be open, because we never know where new ideas are coming from. Put different folks in, and a lot of times it's usually, here's some revision there, here's a counterpoint here, and everything. I'm happy to think about all those things. You can either, there's a link to my email on the channel page. So if you click on it, click for email, you can send me an email there. Or you can send me a message on Twitter or Discord. There should be links below. The Discord might be broken. Just comment if it's broken, and I'll put the link there. I tend to agree with the opposite and counterparts and everything. I don't want to get that woo-woo, but I tend to have a generalized preference that, and again, this is going to kind of sound a little woo, but as above is below, or as below is above, something like that. Because that's the weird thing. If you kind of assume what we originally based the kilogram off of, the density of water, it has a direct correspondence to the meter at that point. So now, again, we have other things there, but it's a very fascinating thing. And there does exist a temperature and pressure, mostly temperature, where water is precisely 1,000 kilograms per cubic meter. The other thing, just if you're using our system, because at that point at that point I would be claiming there's a preferred unit system, which seems crazy that most folks are like, no, that can't be the case. There shouldn't be a preferred basis, because how the heck would you even do water if water didn't even exist there? You get into a super chicken egg thing, but there is a fun thing you can do. Hold on, let me X this out. So just real quick, going into the as above is below. And again, I'm just collecting evidence to help support a particular claim. If the claim's crazy, that's fine. I'll be first to admit that. But where is it on? Share Wolfram Alpha. Screen. So there's an interesting thing. If we take Z boson mass. Actually, no, let's just do the electron mass. Electron mass. Okay. The electron mass, all right, 10 to the minus 31 kilograms. What the heck is that? Ridiculously small. Okay. So the interesting thing is, if we use the system that we have there, and again, this is substantiating that the meter, the kilogram, and stuff would have a preferred basis. If those are the ones of your system, well, I should just be able to take kilogram, square it. So now I'm just taking 1 squared. I'm just taking a reference unit and flipping it by, at this point, what would be claimed the midpoint in your scale. Okay. What do you get? You get about like 10 to the 30 kilograms, which, oh, look, it's a little over the half the mass of the sun. It, okay. Seems to be, what is this? All right, seems to be an M-type star. It's going to end in a carbon-oxygen white dwarf. So it appears to be about the mass of the majority of stars in the universe, typically, or at least what is believed. And again, maybe some of those factors are off, but the interesting thing was, here's the woo-woo thing. You take the Z boson mass. Because that you're like, oh, okay, all right. What is that? 10 to the minus 25 kilograms. You do the same thing. Kilograms squared over the Z boson mass. And okay. Get that? All right. It's 6 times 10 to the 24 kilograms, which, it seems really close to the mass of Earth. I mean, that's just a fun little coinky dink of numerology there. But yeah, no, I'm always looking to look at some other interesting stuff and things that might be going on. But let's see, where are we at? All right. All right. Lucas, what's going on, my dude? What's shaking? How are we doing, my friend? It's good to see you. Good to see you. We still need to catch up. Oh, man. So, Ryan, that actually sounds a lot like my friend Bill's thing that he's got. He's kind of, he was taking the theorized Hawking emission from black holes and trying to extend that generally using the Landauer limit, and basically have some sort of holographic surface being able to represent universe, and as particles, whatever those may or may not be, crossed individual horizons of each other, those would be some form of entanglement or ending entanglement, and then it would be some thermodynamic emission that would lead to gravity or something. So it kind of sounds along those lines. He's got the YouTube channel, Gravity for the Masses. So hold on, I can get Bill's channel is, God, where is it? Gravity T for the masses. Oh, that's a fun little name. Channel. Oh God, parsing. All right. Okay, it's because he doesn't have the. He didn't swap the user ID over. Okay, so yeah, if you want to leave Bill a comment or something, it kind of sounds similar to what he's doing. But if you want to send me a formalized thing, by all means. Oh, absolutely, absolutely. Are you going to the summer school again? Because I remember we were told that if we would like to participate, we should just make it more known. And I don't like to bother people that much. Probably to my own detriment. But absolutely, absolutely, we should catch up again. It'll be very fun. But so Orion, I put that's the link to it should be the Gravity for the Masses channel. That's my friend Bill. So because he has those things, but it sounds like, and again, I'm not a quantum mechanic or anything, but it sounds like that might also line up with some of the things he's doing, and he's kind of just saying, "Oh, there's this contraction and everything," and that raises the other question of, okay, so how's it doing that? Wormholes, ER equals EPR. So maybe he has kind of like some mathematical thing that seems to line up. And again, maybe it's just dimension hopping and stuff. It's like I have my own preferred basis, but what do I know? So it's whatever seems to be moving things forward in an interesting direction that can solve problems. That sounds like a generalized positive thing to me. But hey, maybe you have something that slides right in. You guys could write a paper together, and it would be really cool. See, that's the thing. It's like I personally might have my own positions, my preferred thoughts, like technically a member of the physics monastery, physics monk, so to speak, even though I haven't been to the monastery in a while. It's one of those things. I may have my preferred thoughts and methods to explain things, but just because that's what I personally prefer doesn't mean it's right. That's the thing. So if I run into folks, it's like what you're saying is slightly different words than the person over here is saying. And well, if rather than individuals trying to like, because a lot of times this happens, you'll talk to somebody, it's like, oh my God, I've been working for like years alone on this. I don't have anyone to talk to. Just being able to talk to other folks and just share ideas, that just common interest of humanity. Heck, even if it doesn't arise to anything, it's like, guess what? You're now expanding your minds. You're sharing general human moments. And in the occasional case where you stumble upon something interesting, we can all benefit from that. So that's how I see it. I'm sorry, I got to cross on a diatribe there. It's I like ranting and everything. It's all right. So let's go back to black holes, shall we? Okay, so I did my little numerology there about. It's silly. Maybe I'll do should I do one of those things for like the Ig Nobel Prize or something like that, where it's like you just have a whole bunch of just random things, but it looks interesting. It's kind of fun, and maybe we could do that. It's literally just do the most naive thing. Just go, because we did that exercise at the monastery with that. So let's just take all these things and square kilograms and just see what the inverse was if we assumed this was a thing. It's very, very interesting things there. But again, I'm biased. Pardon. All right, where are we? Okay, over here. Share screen. All right. So I got this. All right, so we'll take a look. Planck density. I keep spelling this wrong. Okay. Oh, we got speed of light to the 5th power. Newtonian gravitational constant squared. And the elementary unit of action, h bar. Reduced Planck's constant. Gives us the numbers we were talking about, basically 10 to the 96 kilograms. It's a mass density. And this is one of the greatest things for any of the different Mathematica Wolfram products and notebooks. And even just Wolfram Alpha. This right here, you just go into Wolfram Alpha for free. I mean, you can get the Pro thing if you want, but it's not required to just do some basic computations. So it's listing here. We got a mass, and it's being divided by a volume, aka we've got a density here. And then if you did this here, if you did the whole c squared, we're going to take the Planck mass, multiply it by the speed of light. So we're going to get the Planck energy divided by the Planck volume, which is going to be the Planck pressure. Because that's what it says there. Or pressure is another word for energy density. What did we do? We just took something with the units Planck mass. Excuse me. We took something with the units of the Planck mass. We divided by the Planck volume, which is the Planck length cubed. And we got that ginormous number. And then all we did was, we multiplied the Planck mass by c squared. And again, that's the rest mass energy. We did not include any of the additional momentum because it's plus mc, and then it's energy squared, and then c to the fourth, and everything like that. Okay. Spherical cow. Spherical cow. Yes, it's simplest case. Idealized circumstances. So when we do that, we turn the Planck mass into the Planck energy. And we did the same thing. Because if you notice, that last thing was like 10 to the minus, or 10 to the 96. Okay. 10 to the 96. All right. C squared gives you about 16 orders of magnitude, because it's like 3 times 10 to the 8 meters per second. So if you multiply a thing with an exponent to the 8th power by the same thing, it's going to go up to the 16th power. It might flip depending on what the actual numbers are up here, but it's going to be about 16 orders of magnitude difference. So just doing that, this should be, I don't know, 16 orders of magnitude, 106. So it should be, 16, about 112, 113. Okay, so it's 113. So, I mean, that's all that's happening. When I first see all these things, it's like, oh my God. It's like a whole new world, a new fantastic point of view. All these words unknown, to me it's Rome, a classical feeling that I'm supposed to yada yada have there. But God, now that I've terrified everyone away and ruined everyone's childhood memories of Aladdin. Oh God, they redid that Aladdin movie. And oh God, I'm real. Wow. That moment when you realize you're old, dude. All right, so I get the Planck pressure. What is that? It's the Planck mass times this. And this goes into the whole cosmological constant problem. What is the cosmological constant problem? All right. Yada, yada, yada. It's where we would expect. It's that 122 order of magnitude difference thingy. Okay. What am I talking about? Okay. So the naive thing, if you assume, basically if you're applying, again, I'm not quantum mechanic. To my understanding is, if you apply quantum field theory and you're going to do all these oscillations and all the infinite number of configurations, basically you're either going to get infinity, or if you're doing a, I believe, ultraviolet cutoff. Basically, if you're cutting it off at the Planck energy, that is the limit, because that's the limit as we seem to know it. But basically, if you cut it off there, you would assume that the energy of empty space would be the Planck pressure. Okay, that's the naive thing. What is it actually? Well, let's type in universe, vacuum, energy, density. Okay. Now, I know this. I happen to know the correct magic words to put in order to get these things to come out. One of the benefits of a lot of LLMs is if you don't get it quite right. And actually, there is a new LLM tool, which, oh, maybe I should just do that. I have access, right? Okay. All right, we'll incorporate that because it's a new tool. We gotta judge it. All right, so the universe vacuum energy density. All right. Well, 5 times 10 to the minus 10. Okay. And this is an energy density. So note, normally if you just have a mass, if you just have a density, it's mass, and we would have a volume here. So basically this would be length cubed because that's what it was before. Go back. Mass, length cubed. Why is energy density different dimensions? So remember, we multiply by c squared. That's length divided by time, and we got 2 of those things. So that means speed is length divided by time. So that means we got 2 things of length coming in here. 2 things of length. So that's going to cancel out. So this is going to go to, this will stay the same. This will be mass. Length will go from -3 to -1, and then time will be -2 there, which is what we have here. Okay. Again, this confused the heck out of me. And even if you learn to generalize units and everything, if you haven't come across the stuff before and you're unfamiliar, like, oh my God, a lot of this stuff is just because we have a coherent system of units and you can go back and forth, back and forth. That's what we were talking about yesterday. We're talking about how you can use 5 constants of nature, big G, Newtonian gravitational constant, h bar, the elementary unit of action, Planck's reduced constant, and the speed of light, the maximum speed of causality, I tend to believe, in a vacuum or in a medium, whatever you happen to prefer. And you need 2 more. You need either, and you can vary your expressions. You need some form of charge, so you need the electric constant epsilon naught, which is, oh God, I need to get this right. Electric constant. It's permittivity. Okay. It's the permittivity of free space. Okay. And then you also need Boltzmann's constant to get a temperature in there. Now, again, you could remove the speed of light and keep the electric constant, swap it for the magnetic constant, because the electric constant times the magnetic constant gives us this thing that as units, we'll multiply, boom. That doesn't mean a dang thing to me. That is an interesting sequence of numbers, though. Now that I'm, okay. Okay, it's the relative mass per energy. Okay, it's the relativistic mass of 1 joule right there. Okay, I'm sorry. Long story short is if you take the inverse, you do 1 over the square root of the electric constant times the magnetic constant. By definition, you get the speed of light. Okay. Hey, yay, we figured out what Maxwell did 150 years ago. But at least going through this, I look at it, I'm like, oh, let me do this. Now it's like, all right, did I do all the hard work that all those other folks did? No. It's like a modern computational calculator that if you have the ability to ask questions, it has a whole enormous database of information that we've gathered, as well as different mathematical constants. And you're going to look at something, and then it's like, maybe we can see something interesting going on. So like over here, hold on, we just take the electric constant, other things here. Okay. I'm sorry. I'm getting off the farm. Let's go back to, okay. That was like a ginormous 5-minute tangent to get to the cosmological constant problem. Okay, long story short is, if naively you would think that the energy of free space would be the Planck pressure, which is this thingy right here. We get 10 to the 113 for pressure. Okay, under pressure. Now, in actuality, the measured value of the vacuum energy density, that's about 10 to the minus 10. It appears to be about, what? About 123 orders of magnitude difference, depending on how you divide it. Because if you take that and you divide it by the Planck pressure. Oh, look, we get a 10 to the minus 123 difference. And then if you divide it the other way and just do one that way, you'll have like about 10 to 122. Yeah. So that's basically the cosmological constant problem. It's like, why is it so different? And I don't know. I mean, I have some crazy, extraordinarily speculative answers, but even okay, I'm diverging too much. It's been a half an hour. We actually need to go into black holes. Okay. So what are we talking about? Okay, let's go to a black hole first. All right. Okay. So long story short is, essentially, if you try to cram a Planck mass into a Planck volume. Okay. So basically, oh God, everything's crazy. All right. So long story short is, in our general conception of what's going on, let's say, assuming at the pressure and temperature where water is precisely 1,000 kilograms per cubic meter, if we had 1 cubic meter of water, it's 1,000 kilograms. 1 gallon of water can be kind of heavy and stuff, and well, that's kind of a lot, but that's something we can grasp our minds over. That's something. It's like, all right, you got a kiddie pool. You might have like 1,000 kilograms of water in a pool. Yeah, you got more than that. All right. Now, if you were going down to the Planck scale, so basically, if you had the Planck mass here, this is approximately the Planck mass. Again, we cut out all the extra things. Just got to know that rough scale, this is 10 to the minus 8. Okay, kilograms. So whatever the kilogram is there, the like 10 cubic centimeters of water, yeah, this is basically the mass of a mote of dust. But if we're going to talk about proton, it's like 10 to the 24 times that. It's magnitudes larger. Okay. This is redonkulously small. This is, I mean, the Planck length is already, what is it? It's like, it's about a million trillion times smaller than like a meter. It's a lot of zeros, my friends. Okay. But basically, if you were to cram a Planck mass into a Planck volume, you're basically going to create a black hole. That appears to be what happens because things stop working and we get a black hole. How does that even work? Neutron stars are absolutely fascinating. Welcome, Poindexter. That was one of the things I remember when I first started watching Professor Keating. I think it was PBS Spacetime did a video on like strange stars and potentially how if given that density, maybe things are shifting off into strange matter, which might be much more stable. And if you had one strange lit piece of this strange matter touch you, it's going to instantly convert everything else to strange matter. But I don't know. Has that happened? I don't know. Things seem pretty strange. Maybe we're just all a whole bunch of complex strangelets or something. Long story short is I had asked him to talk about strange stars, Professor Keating, and I don't think he ever did that because, to be fair, that's basically just theoretical stuff. And if you're an experimental cosmologist, when you're going to talk about stuff that's just like, those are levels that we don't even know and everything. So it's like, if you don't have the knowledge on something, what are you going to do? You can try to talk about it, but then again, I'm talking about all these things. So what does that mean? All right, so black hole, what we're going to do, I should share with the class. All right. We'll just do a formula. I got these formulas here. What does this mean? All right. Hold on. Black hole, 1 Planck mass. Okay. So what do we get? All right. So this, as we can see here, what happens if we try to shove that Planck mass into a Planck volume? Well, it's going to all of a sudden seem to become a quote-unquote hole, or it's a space-time is reconfigured. Whatever is there is just, at least using the Schwarzschild metric without including any electric charge or any angular momentum. And even though basically every single black hole that we have quote-unquote believe we've observed appears to at least be rotating and or has charge. Seem to go a little bit hand in hand. But the primary factor, according to general relativity, is the mass of it. So what happens? Let's go to the little equation here. Okay. So we got 2gm. All right. So we got the Planck mass over there. We divide it there. Now here's the thing. We just did gm over c squared. Let's do that. So let's do Planck mass, big G, divided by c squared. Okay. So basically, we don't have that factor of 2 there. What do we get? Oh, look, we get the Planck length. Here's the weird thing. Here's the weird thing. So normally, if you were to do that, you would think, all right, we're going to have a Planck mass. We're going to have a 1 Planck length radius black hole. That's apparently not what happens. As we can see here, there's a factor of 2. What's going on there? This is the reason why a minimal Planck mass black hole, basically, if you're hitting the Planck density, it's immediately going to at least double in its radius there. Why? I don't have a good reason. That just seems to be how the math works out. Perhaps it's a double cover of something, but now I'm just speculating rampantly and biasly. But yeah, it's interesting that, okay, we go to 1 Planck mass. The horizon radius is not a Planck length. What is it? It's 2 Planck length. I didn't even need to do any extra math. It just told us. Huh. It seems to go up by a factor of 2. Cool. All right. So why am I even speculating about all this stuff and neutron stars? Okay. So let's go to neutron stars. Neutron star. Oh, let's do neutron star mass. There we go. It knows because I've typed it in before. All right. All right. So basically, we're getting ranges. All right. Different units. All right. So let's, oh, we want something more useful. We want its density. There we go. I was looking before and I'm like, wait a second. There we go. All right. So here's what I'm going to conjecture might be a very interesting thing. Okay. Now using Keeling, as we can see here, there's a range for density because apparently neutron stars are one of those weird things that as you add mass to it, it gets smaller. You add mass to a black hole, It gets bigger. For every Planck mass worth of stuff you throw into it, it's going to go rate. Its event horizon radius is going to increase by 2 Planck lengths. That's one of the reasons why, like, an extremely small Planck mass black hole is going to have incredible gravitational effects, especially when you're really close to it and everything. Incredible density, but once you start getting up to like an ultra-massive black hole or something, you might be like the density of cotton candy. Like, it becomes like less than the density of water. It's like, what the heck's going on? But it's just, it's going by that scale that we had there. Because for every Planck mass of matter, it's going to go up equivalently by 2 Planck lengths. That's pretty cool. It's not what we're talking about here at the moment. I'm just highlighting that. But okay, as we can see here, what's the density of a neutron star? Because neutron stars, again, are weird. You add a neutron, it gets smaller. You add more mass, the neutron star keeps seeming to shrink. Why might that be? Well, when we say neutron star, we like to think of it's just a bunch of neutrons. Maybe there's some nuclear pasta, but you start to dive into some of the descriptions. It's like, well, it seems to be a lot of neutrons, maybe mostly neutrons, but there's still like some protons and stuff going around there. So what if you're just adding more mass? You're increasing the gravitational effect more. Well, what if the density just keeps increasing, that it just converts those things into more neutrons? Just, I don't know. Don't we have the electroweak force to do stuff like that? And that seems like a weird thing. I also happen to be of the mind that I've done some minor calculations, and again, highly speculative, more experimental verification roads required. It looks like the radius of the neutron is a little bit smaller than the proton. Seems like a weird thing. Looks to be just a smidgen smaller, starting around the I think the third, fourth significant digit there. And again, incredibly hard to measure, but the whole point of this is I looked at these exponents and they look kind of familiar. Because, okay, if the minimal black hole could have a density that's, where are we? All right. Here we go. All right. So basically, once you hit this density, you're basically going to create a black hole. Okay. Why? Is the universe preventing errors? Is it error correction? It sounds kind of like almost error prevention. I don't know. But long story short is, I looked at this, I'm like, all right, quote unquote, once you hit this magnitude in a Planck volume, you're going to create a black hole. I'm like, okay. So this is a density. This is the limit of density as we know it. Now, I looked at this for neutron stars. Utilizing the same unit basis, seemed to be a 17. And then that made me think there's another Planck constant there that if I took this, let's just do that. Let's do we'll do the interval. We'll just take the high end here. Why? Who doesn't want the high ground? All right, 10 to the 17 kilograms per cubic meter. All right. Let's divide this into the Planck density. Hey, Charlie, what's going on, brother? Oh, yeah, happy St. Patrick's Day to all that celebrate. Okay, long story short is it seemed to be about a 78 orders of magnitude difference. And you're looking at like, it means, what the heck does this mean? It doesn't mean a dang thing to me. 10 to the 78? What the heck could even be going on there? And again, we're in the realm of rampant conjecture here, but hold on, I've got the Wolfram clip here. Let's buckle up as we conjecture ahead. Here we go.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper-rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyper-rulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
So coincidentally, if the reason why that 78 orders of magnitude seemed kind of interesting, because I'm like, okay, Gedonkin experiment time. Gedonkin experiment time. Thought experiment. All right. You have a neutron star. It's in a neutron star state. It is believed that once you hit a particular mass, it will collapse into a black hole. Now, I've heard Stephen Wolfram and maybe a few other folks, I might just be misremembering this, basically conjecture something along the lines of, is there some shock wave or something required within the gravitational collapse prior to supernova, or heck, maybe it just has a direct collapse. There seems to be mounting evidence to suggest that that might happen more than we really have noted. Yeah, it's kind of hard to see something light years away if there's no ginormous cosmic kablooey, right? Okay, so, but basically, you got a neutron star, you got a neutron. How many neutrons does one need to add before it will actually collapse? Is that even possible? But I digress. How the heck could we make hay out of like a 78 order of magnitude? It's not like there's some like Planck unit that's got units that are extraordinarily close or something. Well, unless we did the Planck mass divided by the Planck time squared. I'll give us oh wait, what's it? Oh, it appears to be the Planck spring constant. Or at least what would be the dimensions of the spring constant in Planck units, which coincidentally is mass divided by time squared. It's interesting. Now, again, there's other ways you could say it's a force gradient, linear force density, it's stiffness, surface tension, tear straight, peel straight, spectral radiant energy with respect to wave number, or cleavage. Yes. But I'm like, wait a second. 1.488 times 10 to the 78 kilograms divided by seconds squared. Now, that's not exactly that, but it's kind of close. So, hypothetically, it's, and again, do we know the exact density of these things? Maybe we do. If I was going to take an educated guess about perhaps the maximum density of a neutron star, maybe we need to compare it to the maximum density of a minimal black hole. Oh, wait a second. Can I do that? Wait, black hole. Density of like mass black hole. Black hole is the Planck mass. No. Oh. No, all we do is Planck mass. 4/3 pi r cubed, spherical cow time. Divided by 4/3 pi Planck length cubed. No, it's 2 Planck lengths. Hold on, 4/3. Yeah, 2. There we go. All right. Where's that interval? I'm I actually haven't done this comparison yet, so I'm actually curious. It's probably going to deviate further just because it was pretty close there before. Okay, so it went down to 77. Let's look at it from the inverse perspective. Let's do this. Divide it the other way. Okay, so that's about half the Planck Springs constant. Okay. So, and again, it just happens to match pretty well to a magnitude and everything. But let's see if we can't play around a little bit more. Let's see if any of this actually makes any sense. So let's take our Planck spring constant. All right. Let's just divide it into the Planck density. Again, these are not the same things. We're going to divide out the Planck mass, and now we're going to get, oh God, we're going to get 1 over 3 dimensions of length and 2 dimensions of time, I think. Yeah. Oh. Oh, okay. So we got time squared over volume. That's interesting. Let's do it the other way. Into the Planck density. Well, I mean, probably shouldn't be surprised because that's the root of our Planck constructors. Here, is this equal to the square root of big G h bar c? Yep. Now, if you went through and we do on the board and we cross out all the things, it's just things canceling out. Now, this doesn't really help with neutron stars, but just looking for a potential magnitude. I think if we were looking for a magnitude, we assumed there was there, and that's being extraordinarily generous. Because again, those aren't in the right units. It's just we're putting that there, and we're like, oh look, neutron stars. Okay, it's 10 to the 17. So if I were to take this literally, it would say that the maximum mass density of a neutron star is like 6.88 times 10 to the 17 kilograms per meter cubed. That would give us the Planck spring constant of magnitude. Now, that's not what it is. It does have a volume. It's something within a volume, but it's time squared. I'm not quite sure what to make of that. If it was mass, it's like, all right, there we go. We got a clear answer, but yeah. I'm curious. Let me just take this mass. Just adding dimensions to a numerical magnitude. God, it's so freaking savage. All right, and then let's Planck density. Oh God, hold on. That needs to be kilograms over meters cubed. I almost forgot my dimensions there. Okay, so it's probably going to be, it's going to be 7488. It's going to be like 755, something like that. Probably a little lower. 02. Hold on. Let's just do. What do we need? Okay. Solve for x equals 7.444888 times 10 raised to the 78. All right. X kilogram. Hold on. I need to probably put those in brackets. There we go. So to the point where I just copy this, paste it, boom. All right, so the answer would be 6.88 times 10 to the 17 kilograms per meters cubed for a maximum neutron star density. And again, this is just straight up numerology. I just look at some, I'm like, this kind of looks like a pattern. Maybe there's some there. Now, I can say these words. Heck, maybe we'll pan out. Maybe that is the maximum density of a neutron star. What's a good reason? Oh, it's the Planck spring constant. Cool. Almost nobody knows what the heck the Planck spring constant is. Heck, a lot of people don't even know what a spring constant is. I didn't even go through all the physics. It's like, all right, you got the block. It's attached to a spring. It's on a wall. It seems to be moving a distance, but also you model that distance with its time interval. And it seems to be we have like a minus prefactor in there as well. Yeah. So mean density of 3 times 10 to the 16. Mean density inside the Schwarzschild radius of a supermassive black hole. That's about 20 kilograms per meter cubed. Wow. So that would already mean a supermassive black hole is less than the density of water. Interesting. Okay. So now if we had a lot of these digits are just making those up. We didn't have that much information. Just kept running it as all zeros. So all right. So Planck density. There we go. That's the Planck spring constant. Now, again, even this numerology did pan out. Can you explain? Well, why are you saying time squared could have anything to do with mass? I don't know. That's for somebody other than myself to conjecture away. And again, this is simply rampant speculation from a crazy person on the internet. I thought it was kind of cool just because I'm like, all right, we got the right magnitude. All right. If according to that, like 6.8, it appears to be 5.9. Doesn't seem to be much further. The equation of state of neutron stars is also not well known. I mean, this seems to be probably one of the best things here. It's not well known. Why? Well, apparently once we get past just hydrogen itself, and we start to try to calculate stuff going on with other particles or wavicles and stuff, it gets really hard really quickly. So yeah, if we're trying to deal with, listen, we got enough trouble dealing with like a single mole of things. So that's like 10 to the 23 entities. Yeah, that's within like a gram of stuff. Yeah, try doing it with what is it? Oh god, how many neutrons in a neutron star? How many neutrons in a neutron star? I don't even know if it's probably well formulated in AAIH. Okay. All I know is it seems to be very difficult. So listen, I just look. I see magnitudes. This looks kind of close to this. How close does this get? How well do we know the things? All right. So I'm just like, well, this block seems to fit here. Now the logical dimensions behind it, maybe it doesn't line up. Just seems to be a proportionality thing. So many things seem to line up so well. Maybe there's some there. But again, I don't have any good reason for that to be the case. So as far as I'm concerned right now, it's kind of like saying like, okay, kilogram over the electron mass. Oh, look at this. Oh, look, hey, it gives you out kind of like a common star type, or doing like kilogram squared over the Z boson mass. Yes, it's a neutral boson there. It doesn't have any charge. It seems to be the carrier for the weak magnetic force, or one of the carriers. And when you take kilograms squared, you divide it by it, you get about the mass of Earth. I don't know. It's and again, it's numerology. That's all that is. I'm just looking for characteristics. If somebody has a better idea, if somebody's got something to add, or all of a sudden this helps somebody and somebody's like, oh my God, I've been thinking about something like this for a long time. Cool. Just think about us when you're famous. That's all. But yes, thank you. Yeah, listen, whatever you want to do with this content, if you can enjoy it, feel free to interact however you want. Hit whatever buttons. You can spread it around however you want. I hate the whole like comments. I don't like telling people what to do, but feel free to hit whatever buttons you want in this. If you enjoy this, if you hate it, by all means, do what you got to do. But with that said, thank you all for watching. Peace out, everybody. Take care of yourselves. It's a wacky and wild world out there, but it's open for a better tomorrow, y'all. So you can all level up.